point, we have learned derivative formulas for any combination of functions whose derivatives we know that uses arithmetic. We've got the sum rule, the difference rule, the product rule, and the quotient rule. So that corresponds to the 4 arithmetic operations. The other main way that we have of combining functions is function composition. So that would be when we have f of g of x. So we're plugging the result of one function, g of x, into another function. As an example, let's just suppose that g of x was equal to sine x, and f of x is x squared. Now here it's really important that I recognize that x is just a placeholder for my input. So that when I look at f of g of x, I can see that what's inside the parentheses after the name f is g of x. And what g of x is sine of x. Okay. So f tells me to take my input and square it. This would be having me take sine of x and square that. Okay. Now, we often will write that, as just sine squared of x. That way we don't have to write the parentheses, because if you're writing things a lot, it's easy to accidentally drop the parentheses. Notice the exponent comes after the sine, so we are not squaring x, we are squaring sine of x. And some of you may find it helpful to rewrite this as sine of x quantity squared. That just makes it a little bit easier to see that sine of x is the inside part, which is our g of x. Now when we do function composition, we're basically doing an assembly line for things. So I'm going to represent each function as a machine that I'm just drawing as a rectangle. This is the function g. And with a machine, you input something, and then that outputs the result. And then we pass that along to the second function, and the output of g becomes the input to f, which will spit out something else. So with our particular example, g we said was the sine function. So whatever we plug into g, we're plugging into the sine function. F, we said, was the squaring function. So whatever we plug in, whatever we get out of g, we plug into f, and we square that. If, just as an example, I were to take pi over 3 and plug that in, pi over 3 gets plugged into sine, so I would take sine of pi over 3. That's root 3 over 2. That's the output from g. That's going to become the input to f. So I would plug in root 3 over 2, and I would square that. And so that becomes, that just becomes 3/4. One thing I want to emphasize here is that the numbers that I'm plugging into the two functions are not the same. Here I plugged in pi over 3 to g, but I plugged in root 3 over 2 to f. Okay? So that's different from when we combine functions with arithmetic. When we combine functions with arithmetic, we're plugging in the same input to both functions and then just combining the results using arithmetic. With composition, my input to each function is different. The input to the outside function is actually the output of the original function. Okay. So I'm going to go back to just sort of a generic picture. We'll come back to this particular example in a moment. But with a function composition, I would take x, I would plug that into g. What that spits out then is g of x, and that becomes my input to f of x, so that the ultimate output is f of g of x. And what we're trying to figure out now is how to take the derivative of f of g of x. Okay. Well, before I tell you what the formula is, I want to just think about some things that seem like they're relevant to this question. What I'm trying to get is the rate of change of this output with respect to this input. But creating this output was a two-step process. The first step I plugged into g. So if I were to change x, that's probably going to change the output of g of x. Okay? That's going to be measuring the rate of change of that first step. But then I take that and I plug it into f. So if I've changed x, that's changed this, that's going to change the output. So it's a two-step process. There are two functions that are going to contribute to this rate of change. So it kind of seems reasonable that the function that measures the rate of change at this step is the derivative of g. So it seems reasonable to me that g prime ought to play some role in describing the rate of change of f of g of x with respect to x. And I care about g prime at x because that's what I'm going to be plugging in. Okay. Now for the second step of the process, I'm plugging into f. The function that measures the rate of change of f is f prime. So it seems reasonable to me that f prime ought to somehow be part of the description of the rate of change of f of g of x. Okay. But what's interesting here is I don't care what f prime is at x because I'm not plugging x in to f. What I'm plugging into f is g of x. If you remember, when we had our example with numbers a moment ago, we plugged in pi over 3, and then we plugged in root 3 over 2. Okay. So I didn't care how the squaring function was changing at pi over 3, because I wasn't squaring pi over 3. What I was squaring was root 3 over 2. So it seems reasonable to me that I should care about the rate of change of f at g of x. So I've got two functions, g and f. I've got two derivatives, g prime and f prime. I'm going to evaluate each derivative at whatever I was plugging into that function. So if I'm plugging x into g, I want to care about g prime at x. If I'm plugging g of x into f, I'm going to care about f prime at g of x. Now, all I'm doing right now is sort of suggesting why this seems reasonable. I'm not doing a formal proof of anything, but I just want you to see some of the logic behind this. We're not going to do a formal proof of the chain rule. It's a little bit harder to prove than the arithmetic rules. So I'm just going to stick with this informal suggestion. But it turns out that what I've suggested is correct, that both of these derivatives are going to be used in building the derivative of the function composition. And it turns out that what this formula is that this is just the product of those two things. F prime evaluated at the input to f, which was g of x, multiplied by g prime evaluated at x. Okay, kind of cool. Okay, now what I haven't done at this point is explain why we multiply them. I've just sort of suggested that it should be reasonable to you that both of these would be relevant to the formula for the derivative. And now I've told you they are, and in fact they're connected by multiplication. Okay. So in the next video we'll explore a little bit why we actually multiply those. What I want to do right now is just go back to this problem right here and evaluate this particular derivative. Okay. So if I wanted to take the derivative of sine of x squared. Notice g of x, the inside part was sine of x, so g prime of x is just going to be cosine of x. F of x was x squared, so f prime of x is just 2x. Okay. So when we use the chain rule, I'm going to work my way from the outside in. The outside function was the squaring function. That's the last thing I would do here. So I can say the derivative of the squaring function is that I double my input. So I'm going to get 2 sine x. Notice that's f prime evaluated at sine x. I'm not evaluating it at x, I'm evaluating it at g of x, at the input. And then I need to multiply that by the derivative of the inside part, which was sine x. Okay. Often, because this first step is a little bit complicated, I've got to take a derivative but evaluate it at the inside part. Often I'll just use this d by dx notation so that I'm really focusing on that first step and then just acknowledging I got to go back and do that second step. So then I would say, okay, so this is 2 sine x times the derivative of sine x is cosine of x. Okay, excellent. Like I said, in the next video, although we won't be doing a formal proof, we'll talk a little bit about why it is that we actually multiply these two derivatives together.